Alright, so in this video I'm gonna be explaining another important article with the title Maximum Independence Set, Self-Training Through Dynamic Programming. This NeurIPS paper in 2023. This work presents graph neural network framework for solving maximum independence set problem. Inspired by dynamic programming. Specifically, given a graph, we propose a dynamic programming like recursive algorithm based on GNNs that firstly constructs two smaller subgraphs, predicts the one with the larger MIS, maximum independence set, and then use it in the next recursive call. To train our algorithm, we require annotated comparisons of different graphs concerning their maximum independence set size. Annotating the comparisons with the output of our algorithm leads to a self-training process that results in a more accurate self-annotation of the comparisons. So we present our approach for developing algorithm for MIS parameterized by parameters theta. We present how any graph comparing function taking as input two different graphs and outputting a 0 or 1 value can be used in the construction of an algorithm computing an independent set. We present how graph neural networks can be used in the construction of such graph comparison functions. So the input is just two different graphs. We consider a function from two graphs, graph 1, graph 2, to either 0 or 1 that compares the two graphs based on the size of their maximum independence set. So if size of maximum independence set of G is greater than maximum independent size of G prime, then this function is 0, otherwise is 1. So the theorem 1 ensures that if we have access in such graph comparing function, then we can compute an independent set of maximum size for any graph G from a starting node P with an initial graph from G, and by recursively selecting either G based on the cardinality of maximum independence set greater than cardinality of maximum independence of G, and we are ensured to end in an independent set of maximum size. So the decision whether this holds at each recursive call can be made according to the output of this comparison function. Here you see a randomized comparator-induced algorithm that we take a graph G as input, and then we return A. We remove the neighbors of V, remove vertex V. I will explain. So the cornerstone idea of our approach is that any graph comparing function induces such a recursive algorithm for a MIS, maximum independence set. Recursively, they can be based on the output of a graph generating function, always guaranteeing to reach an independent set of original graph. So a comparator is a function that takes two graphs G and G prime and gives 0 or 1 value. A comparator induces a randomized algorithm A that we discussed. So this is a randomized algorithm A. because the algorithm A takes a graph G as input. And now, what are the comparators? Comparators through graph neural networks. So we discussed the architecture of a model M, which is parameterized by theta from graph to real number, that is used for the construction of the comparator. Because if we have this function M, then we can use it to create our comparator function. So we just need to create this function from graph to R. But how do you create such a real number from a graph? Well, you know that there are many approaches, and in order to embed graph-level information, we introduce a new GNN module, which we refer to as Graph Embedding Module. Unlike standard GNN modules, this module captures different semantic meanings of differing embedding of a node, its embedding and anti-neighbors. The GEM operates using the following recursive formula. So all nodes in this graph have zeros embeddings. Mu sub v denotes the initial embedding vector. And for all iterations, the embeddings of a node, its neighbors and its anti-neighbors are put through their own linear layers. And the bias term is omitted in the equation for readability purposes. We incorporate anti-neighbors in the GEM to capture complementary relations between nodes. So we are concatenating these. So the architecture of model M is shown here. That from left to right, we see that first an input graph G is passed into the model with zeros as node embeddings, which are displayed as white in the figure. The stripped green edges, these green edges, connect the anti-neighbors. You see even the anti-neighbors like V5 and V2, they are connected to each other. So, connect the anti-neighbors, which are also used in the GEM. After k iterations of the GEM module, the final node embeddings are obtained. These are then averaged to obtain a graph embed. Everything is fine, except this one, which is compromising to the world, because you are losing the topology of the graph, so you are ignoring an important source of information. It's a global pooling, but everything else is good. So we discussed how a parametrization theta defines the graph comparing function. As a result, the same parametrization defines an algorithm. The key idea to overcome the latter limitation is to annotate the data of the form by using the algorithm that runs in polynomial time with respect to size of the graph. Intuitively, our proposed framework entails the optimization of the parameterized comparator function on data generated using algorithm. A better comparator function leads to better algorithm, which leads to better data and vice versa. This mutually reinforcing relationship between two components of our framework is theoretically indicated by Theorem 2. Here we introduce a notion of consistent graph comparing function that plays a critical role in our self-supervised learning approach. Kindly take note that A utilizes the unparameterized variant of a comparator function, whereas AC, this utilizes parameterized counterpart. So a graph is called consistent if and only if for any pairs we have this relationship. So the goal of training is to find parameters such that this holds. Exactly the same thing that we have in this here. And the cornerstone of our approach is a self-supervising learning, which makes the comparator more and more convenient over time. So we first set two hyperparameters, one that specifies the number of graphs used to populate the buffer before training module, and another determines the number of graph pairs generated from a pair graph. Then a dataset is created by generating these pairs for the set number of graphs. You see an example of data generation for the training. At the beginning of each training is algorithm 2 samples the graph and computes an independent set by using the comparator, and by following the branches in the recursion tree that are marked red with the doubly circled one being the produced independent set, the generated graphs from this procedure are added to the buffer. Then a dataset is created by sampling graphs from the buffer and then computing an estimate of their MIS size. Based on this estimate, the dataset is created with graph pairs and their corresponding binary labels denoting which MIS estimates are larger. You see a distribution over graphs. We initialize parameters, initialize a graph buffer, and we run A and store in B all graphs produced during each recursive call. Then we update the parameters as this that I explained. We update the parameters, and we do it, of course, for all epochs. So we compare against neural approaches like Erdos GNN